So I'm going to go through some main points from Bill Gates's new book, just came out maybe a month ago or so. How to avoid a climate disaster, the solutions we have and the breakthroughs we need. Fortunately, his ideas map onto what we saw in Drawdown and in designing climate solutions, and yet the perspective is somewhat different, so it's worth looking at it again. So he starts with this figure, which we have seen several times. So the expected global warming with the different trajectories of emissions. Business as usual, high emissions would take us to close to 5 degrees or more by 2100. And there are lower emission trajectories which will keep us below 3 degrees maybe, but still above the 2 degrees that is argued to be desirable. As I have commented before, that's not really a totally scientific target, but it started with Bill Nordhaus in the 1970s in his economic calculations, the climate casino and the DICE model he has, and he won the Nobel Prize for his climate economics ideas. And so Stern Report picked it up, European Union picked it up, and now IPCC has picked it up. And IPCC also came up with a 1.5 degree emission scenario as even safer than 2 degrees centigrade. But that would require that by 2100 we essentially be in negative emissions. And I think I already mentioned that this doesn't mean actually negative emissions. It just means there are some unavoidable emissions, and then we take out more carbon than we put in. And Bill Gates argues that it takes really a long time to adopt to new sources of energy, and he relies on a nice book by Vaclav Smil called Energy Transitions. There are many studies on socio-technical issues associated with such transitions. So if you look at the global energy supply percentages from coal, for example, from the Industrial Revolution to the beginning of the 20th century, it reached a peak of almost 50%. From 1910 to 1970, oil picked up and reached peak production of 30% of the global energy supply. Natural gas, which is much more friendly than oil, which is much more friendly than coal, carbon emission-wise per energy unit. And here we are with modern renewables, let's say starting in 2015. So we have a long way to go, and there are many issues of people switching to these, and we have talked about these in terms of also systemic changes needed in terms of grids and microgrid, smart grid, and so on. Other than the technological innovations for making the renewables themselves more efficient and less costly, which is very steadfastly headed there anyways. The idea that Bill Gates brings in is something unique. He puts a premium on switching from these cheaper, easily available sources of energy to more environmentally friendly sources that have to take us to net zero. So how much greenhouse gas is emitted by the things we do? This brings us to the kind of things we have already looked at under Drawdown, for example, making things. So cement, steel, and plastic, they are the big things that are environmentally quite unfriendly, 31%. There is the plastic pollution aspect, which is separate. This is just about manufacturing them. Plugging in, so energy production and electricity we use for various things, that's 27%. Growing things, plants, animals, land use, agriculture, livestock, meat, fish, etc., 19%. Getting around, transportation, planes, trucks, cargo ships, 16%, and keeping warm or cold, so heating, cooling, refrigeration, which is at 7%. So obviously this is a slightly different way than the way we looked at under Drawdown, but obviously the same phase space, and we can map things onto there. So how much energy does humanity actually use? The world is around 5,000 gigawatts. You can convert it to terawatts, terawatt hours, and other ways that people look at. United States is at 1,000 gigawatts by the time this book is written. Mid-sized city would require about 1 gigawatt, a small town at 1 megawatt, and average American household uses about 1 kilowatt. Obviously, this depends on where you are in the world, but nonetheless, that's a good measure. How much power can we generate per square meter? So this is an interesting and good point in the sense we are hankering a lot about solar, renewables, hydropower, wind, wood, and other biomass. But if we just look at these sources of energy in terms of watts per square meter, right? That shows a tremendous difference. So fossil fuels generate 5,000 to 500 to 10,000 watts per square meter, okay? Whereas nuclear is 500 to 1,000. Solar is only 5 to 20 watts per square meter. So when somebody says solar or wind can replace everything else, then the key question is how much space would that require? And that's not trivial. Hydropower, 5 to 50 watts per square meter. Wind, just 1 to 2 watts per square meters, and wood and other biomass less than 1. So it's not just about how much carbon drawdown is going to happen, but how it's actually going to be accomplished in terms of the space you need. So if you then use these numbers and try to convert it into the kind of energy kind of space we would need for solar and wind, then you can imagine that just an American household would require huge amount of space. And then there's the idea that we cannot get to net zero in any case without having some kind of a carbon drawdown. We talked about direct air capture, for example, and other methods like enhancing sinks in land, afforestation, reducing deforestation, etc. But if you just conservatively assume that it would take $100 per ton to draw down carbon, and we are at 51 billion tons per year now, and let's say it remains somewhat the same through to 2050 or 2100, then you are looking at $5.1 trillion per year in terms of the uh, most conservative cost, but of course this number is much higher depending on where and how you do it. So that $5.1 trillion is around 6% of the world's economy as of now. That is much higher than most people would be willing to invest in drawing down carbon. Okay, so I will leave it this first part here and then run through the various chapters on how he looks at the premium on green economy on the various switches we have to make for the table that we looked at here. So if we look at these few things, how we make things, how we use electricity, how we grow things, getting around and keeping warm and cool, and look at how much reduction has to happen to get to net zero, then that'll give us a sense of what the challenge is that we are facing, right? So let me come back to that in the next podcast.